In this video, I'm going to talk about radiation and half-life. It's part of topic 7 and is SL material. It's about using simple calculations to calculate with half-life, and I will only use integer values of half-life. I'll have a separate video later that will use the decay constant and equations to calculate half-life for the HL 12.2 syllabus. So take a moment and read the success criteria that we will go through in this video. Okay, before we go any farther, let's make sure everybody understands what half-life is. So it's the time it's going to take for half of the nuclei to disintegrate or undergo a radioactive decay. And because the radioactive decay is random and is spontaneous, we can't actually figure out which atom's going to decay next. We actually can't even force it to occur. That's why it's spontaneous. So what can we do? Well, we can actually come up with some probabilities of when an atom can decay. And if we have a large enough group, we can be pretty close to saying, all right, in this amount of time, half of them will decay. Which ones? I don't know. It's kind of like having a room full of pregnant women. You know that they're going to give birth, but you can't actually predict which one's going to give birth when. And then you can't even say, is it going to be a boy or a girl? But if you have a large enough number of ladies, you could say that of these births, probably half will be boys and half will be girls. Okay, so we can't actually do it for a single atom. We can only do this for a large number of atoms. The other thing is here I have for a definition is that the activity could be reduced by half. And what we mean by activity is the number of decays per second. And if I have more nuclei, then I'm going to have more of them decay. So they are directly proportional to each other. Now, if I graphed it over time, how many nuclei I have, or in this case, I'm showing how many the activity here, because I can measure this, but really I can't count the number of atoms. And I look at it over time, I will get this exponential decay curve. Now, this one starts at 40, and then I can see where it goes to 20, 10, and so forth. And notice that it's a constant amount of time every time it decays by half. Now, one thing I want to point out is that we're not just talking about if we start at time equals 0 with this value of 40, for example, in this case, the original number of nuclei. So if I actually took and put some other numbers on here, so if I put, say, 30 here, and I did the same thing, and then I went down to 15, and you can see I'm just doing this by hand very quickly. But what I want to point out to you is, look, that's a half-life as well. It could be any value that you start over here and then find out where it's gone to 1/2 the value, and it will still give you the half-life. And if you were doing this from a graph and you had to calculate it, this part here where you see the most curve in the line will actually give you the most accurate answers. At the beginning where it's really flat and at the end where again it flattens out, those are very difficult to get very accurate values. So try and get your values in the center, in the curved part. So the SL does not have to do a calculation here, but I just wanted to point out, you can see here I've got a line of best fit with this data, and you can see that it is actually an exponential decay. I have seen some people put half, 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 but this decay is actually better represented with the exponential decay. So what I have in the next few slides are a few different ways that we can actually think about how to determine half-life or how to use half-life. So in this example, I've got a table and all the data is in the table. And the question asks, using the table, what is the half-life of the radioactive material? Pause the video and see if you can find the answer. Okay, so if we take a look here at the count rate, I have 80 to start with, and then it goes down to 40. That takes 2 minutes. If I go from 40 down to 20, it takes another 2 minutes. Notice that I could also go from here from 56 to 28, 28 to 14. It should work. So no matter what, my answer will be 2 minutes. Okay, here's the next one. Half-life of a radioactive sample is 5 hours. A sample is tested and found to contain 0.48 grams. How much of this substance was present in the sample 20 hours before the sample was tested? Hit pause. Remember, do this for yourself first and then check to see if you got the answer. I'm going to start off here with 0.48. I'm putting it over here because this is time now, but I'm looking how far back 20 hours were. So if I go back one half-life, that's 5 hours, I'm going to get 0.96 grams. If I go back another half-life, another 5 hours, 1.92 grams. Now I'm just doing this quickly in my head, so forgive me, but in this case, if I go back another 5 hours, 3 point something or other here. If I go back another 5 hours, I'm going to get 7 point something or other here. Now, I don't really need to know those exact numbers, but I have now gone back 20 hours in total. Okay, so notice here, I have 5 different numbers, but I actually only have 4 different half-lives. And I do recommend you do this kind of diagram when you answer these questions. Let's go look at the answers first. Well, if I was getting a sample 20 hours before I had the 0.48, there's no way it could have been A or B, because that's less. And this is decay, so I must have had more than 0.48. And now here's where they're tricking or making sure that you understand the idea of half-life. If you just went back so many numbers, you wouldn't have got the right answer. And now I know what my dots are supposed to be, 0.68. Okay, slightly different question. A small amount of a radioactive isotope contains 72 billion unstable nuclei. The half-life is 4 hours. So how many unstable nuclei would remain after 12 hours? Pause the video and find the answer. Now notice all of these have the word billion in them, so I'm just going to ignore these so I can use nice, easier numbers to deal with. And I'm starting with 72. Half-life is 4 hours, and that will bring me down to 36. Another half-life would bring me down to 18, and then to 9. And let's just double check. I need half-life is 4 hours, and I need 12 in total. Oh, there I go. Answer is B. Let's see if you understand how things are changing. A sample of radioactive 236 uranium has a mass of 1 gram. Another sample with the same material has a mass of 2 grams. Which property is the same for both samples? Pause, think about it, and come up with an answer. Okay, so let's think about this. They have 2 different masses, so that's because they have different numbers of uranium atoms. It's not going to be the same. That being said, 2 different masses have 2 different volumes. So let's think about the amount of radiation emitted per second. That is the activity and the half-life. Now, in the previous part, we already said that the activity is proportional to the number of nuclei. And if I have 2 grams compared to 1, I have more nuclei. Therefore, the activity is going to be different as well. So let's think about this. Why does half-life make sense? Well, it's an intrinsic value, kind of like density. It doesn't matter if I have 10 grams of gold or 200 grams of gold, it's still going to have the same density. It doesn't have the same mass, doesn't have the same volume, but it will have the same density, irrespective of how much there is. Okay, if 1/8 of an original sample of Krypton-74 remains unchanged after 34.5 minutes, what is the half-life? Pause, do some calculations, and come up with an answer. Okay, so if I have 1/8 now, that means one half-life before that was a quarter, a half-life before that was a half, and 1. So if I have 1/8 left, and this whole time took 34.5 minutes, well, there's no way a half-life can be 46. Why? Because in 34.5 minutes, I'm down to much less than a half. Likewise, it can't be 34.5. Now you can see my little loops there. After 1/8, that means it must have gone through 3 half-lives. And if I take 34.5 and I divide it by 3, I will get 11.5. That is our answer. One last question. A sample starts out with 100% undecayed nuclei. What is the ratio of undecayed to decayed nuclei after 3 half-lives? Please pause and try and calculate it out first. Okay, so here we are at time 0, and we have 100% undecayed and 0 decayed. After 1 half-life, I'm going to have 50, right? Half of them will have decayed after 1 half-life. That means 50 over here. After 1 more half-life, I'm going to be at 25, 75 over here. Now I need 1 more half-life, 12.5, 87.5. Now this isn't any of the answers there. So what we need to do is we need to look at these and put them into the lowest ratio. So 50-50, that is the same as saying 1-to-1. 25 to 75, that's 1-to-3. And the last one, 12.5 to 87.5, that's 1-to-7. So sometimes you're given values in a graph. Sometimes the values could be in a table. We've seen examples that had fractions. We've seen examples that have ratios. But all of them in common would be with integer values of half-lives, like here, 3. You didn't have to do 3.5 because it's not actually going to be halfway in between because it's not a linear function. All of these different style of questions, you just have to stop yourself and say, what kind of diagram or model can I write down to help me realize, am I decaying? Am I going into the future? Or am I looking for how many used to be there and come up with our answers? So please go through the success criteria one more time to see if you can now do all of these things.